Thank you very much. So my first talk is going to kind of be a beginner's guide. To monoidal categories. I kind of feel I'm a little bit the outlier in the workshop this week. So I think a beginner's guide to monoidal categories is probably the thing to start today. So we're very fortunate that there's now an absolutely beautiful book by Ettinghoff, Jelacki, Nikšić, and Ostrich, which you can all download from Pasha Ettinghoff's webpage, because the PDF of this book is there. So everything that I get wrong, you can look up in that book after the talk. And it's really a beautiful book. So this subject suddenly becomes kind of open to everybody to use this language. Okay, so always I'm going to work over a field K, and everything will be K-linear. I won't even say the word K-linear ever again. So let's let C be a category. I think it's worth thinking about a trivial example of a category. Let's think about a category with one object. So there's only one object, and then what are morphisms? Well, they're endomorphisms of that object. That's an algebra. Everything's K-linear. So that's just a K-algebra. Let's call that object, I don't know, dot. That's the same data as the data of an algebra. A, that's just the endomorphism algebra of that object. Let's maybe just have a silly dictionary here, because I'm going to try and talk about categories, but it's helpful to be very concrete and think about this kind of most stupid example. So let's remember that if you have that algebra, you can look at the category of modules over that algebra, A mod, and there's this, we all use the Yoneda embedding all the time. And so it's a kind of a dictionary from the category language to kind of simple ring theory language. So this is an embedding of, I guess is probably contravariant, of the category C into the category of A modules. Now this is a very stupid example because there's only one object. And of course that maps to the left regular module, AA. And then if you have an endomorphism of that object, that's just an element of the algebra A, that's meant to map to an endomorphism of this module, and what is it? So it maps to right multiplication by F, and because it's right multiplication, that's why it's contravariant, this business. You see, I want to tell you about two constructions just before we go anywhere, which are going to be kind of crucial for the whole point of view. I think everybody probably knows these constructions, but the first construction is very easy. It's called the additive envelope. So I'm telling you this in the general framework. So C is any category. There's always this additive envelope, add C. And so the objects of this, they're just finite direct sums of objects. So let's just think of them as finite column vectors of objects of C. And then the morphisms, they're just matrices of morphisms. Right? So everybody knows that construction. In this kind of little dictionary to kind of old-fashioned algebra, let's just think what the additive envelope of this one object category corresponds to. It's Yoneda, so I should probably put an op there. So I should be able to realize it as a subcategory of A mod, because this is additive, and it's just the finitely generated free modules, right? Because we've got the regular module, and now we've got finite direct sums. So we've got finite direct sums of the regular module. And the second general construction that I'll use a lot is the Karoubi envelope. I think when I'm writing papers, I call this the additive Karoubi envelope, because I mean the Karoubi envelope of this guy. So I'm doing, so this, but I'm just going to simply write char for Karubi. So it's going to be additive, and Karubian just means idempotent complete. Every idempotent splits. And so this is another kind of very simple, so the objects of this guy, the objects of this are pairs of objects of the additive envelope plus an endomorphism of that object, which should be an idempotent. So the objects of the Karubi envelope are pairs x, comma e, where e is an idempotent. And then morphisms are just morphisms between the x's that commute with the idempotents on each side. So really you're just adding new objects that correspond to images of idempotents in the original objects. And so again, in our little dictionary, what is the Karubi envelope under Yoneda lemma, under Yoneda embedding? Well, that's just finitely generated projectives. So you take finite direct sums of the regular module, and then you take images of idempotents. So you're taking summands of finitely generated free modules. So that's finitely generated projective. Okay, so don't be scared of additive and Karubi. I'm going to use them a lot. Okay, so C is any category. And actually what I want to tell you about is end C. So this is endofunctors F of C and natural transformations. Maybe I'll use like Greek letters alpha, so that might be a natural transformation between two functors F and G. Okay, so this is a new category. So the category of endofunctors from C to C, and then morphisms in this new category are natural transformations between the... Say that again? That's what I meant. Yeah, I mean, when I said Karubian, I meant the idempotent completion of add C. I thought I pointed out that I was going to make that a little... honestly, I call it the additive Karubian envelope if I'm writing papers. Okay? So yes, additive and it's idempotent complete. So back to this category of endofunctors and natural transformations. So I'm going to draw pictures. Here's how I'm going to draw the picture of a natural transformation alpha from functor F to functor G. Because I'm going to put this little coupon with alpha in it. So my pictures, you always read them upwards. This goes from F to G. Okay? And let me see. So what's composition in this new category? So how do you compose two natural transformations? So this is called vertical composition of natural transformation. So let me see if I can... squeeze in a little picture here. So I don't know, if I have a functor F and a natural transformation alpha from F to G, and another functor H and a natural transformation beta from G to H, vertical composition, this will be beta composed with alpha. That's how I'll write it. So this is composition in this new category. And it's meant to be a natural transformation from F to H. Okay, so I'm just kind of getting used to this diagrammatics a little bit. That's, yeah, beta composed with alpha goes from F to H. And what is it? Well, this is easy. To tell you a natural transformation, I just need to tell you what it does on an object. It should be a morphism in the original category on object X. And this is just whatever the natural transformation beta is on X, composed with whatever the natural transformation alpha was on X. Okay? So this goes from Fx to Gx, this goes from Gx to Hx. That's the vertical composition beta composed with alpha. Okay, but this is better than just being a category, this category of endofunctors and natural transformations. It's actually a monoidal category. That means that there's a functor called tensor, which is going to be a functor from this category NC cross NC. Oh, there should be a D in there. NC. So I need to be able to take any two objects in this category and tensor them together. So I need to be able to take two functors and form a new functor called G tensored F. And this is, actually, I usually just write this GF. That's just G after F, do one functor after the other. But I also need to be able to take two morphisms and tensor the morphisms together, because this is meant to be a functor. So I need to take two natural transformations. Let me see, maybe, I guess I better get my, let's draw a picture for this. And so there's a natural transformation alpha from F to F prime, and I'm going to take another one, beta, from G to G prime, and what I'm trying to tell you is what is beta tensor alpha. So this is called horizontal composition. Of natural transformations. This is a little bit harder than vertical composition that we had before. Actually, you know, I usually just write this beta alpha. I omit the tensor symbol when I'm working with natural transformation. So this is the picture, beta tensored alpha, right? So you see the tensor product is sticking things horizontally. Composition up there was sticking things vertically. Okay. I need to tell you what beta alpha, let me see if I can get this one right, on X is. So this is meant to go from, so beta alpha is meant to go from GF to G prime F prime. Okay, so on a given object X, this is meant to go from GFX to G prime F prime X, right? So I need to tell you what this is, and let me see, what can we do? We can, so we've got alpha X, which goes from Fx to F prime X, and we can apply G to that. So this now goes from GFX to GF prime X. And then I can do beta F prime X composed with that, because that goes from GF prime X to G prime F prime X. Okay, so that's the definition of that guy. And you can also write it this way. That's a little exercise. It follows from naturality. That's that equality there. So this is you know, well, maybe I won't go too far there. So I said this was the tensor functor. I told you how to tensor together functors and how to tensor together the objects and the morphisms in this category. And this equality is kind of important, because if you actually want to check that it's a functor, then, well, you'll need to use that. And I'm not going to do that now. Okay. So the main thing to take from that is these pictures. I'm going to draw pictures for everything. So vertical composition and horizontal composition. So this monoidal category is actually a strict monoidal category. So that means that if we have three functors and we tensor them together, well, there's two ways to do it. It turns out that it doesn't matter when you tensor three functors. It's still just the composition of the three, and the definition of a category is that H after G after F. Yeah, composition is strictly associative. So that's what strict means. It means there's simply equality there when you do this tensor functor in the two ways that you can put it together. I should say there's also a unit object in this category of endofunctors of C, and that's just the identity functor. And you know, the identity functor composed with any functor is simply equal to that functor. So again, those are just equalities there. That's all part of what strict means. So this category would be very important. This is where monoidal categories come from for me. They come from endofunctors and natural transformations of other categories. Maybe we should talk about a more basic example. Because I kind of started with a sort of fancy example, this category of endofunctors. But of course, you all know the category of finite dimensional vector spaces. So I'll just write vec. Let's put vec means finite dimensional vector spaces. And you all know tensor product of vector spaces. If I have vector spaces x, y, and z, you can tensor them together. That's your tensor functor. You know how to tensor together linear maps as well. But actually, at least when I was taught tensor product, those two are not equal. It's simply not an equal. The definition of tensor product is that they're sets, and the underlying sets are not equal sets. So instead, all you have is a natural isomorphism here. So, you know, in kind of proper tensor categories, like proper monoidal categories like this one, they're not strict. The associative doesn't hold on the nose. You need some natural isomorphism that's called an associator. And the same thing goes with unit. You need some natural isomorphism called uniter. Of course, the unit object in Vec is the field K. But, you know, it's like K, tensor to vector space. It's not equal to the vector space. It's merely naturally isomorphic to the... But apart from this one, I think all the other examples of monoidal categories that I'm going to show you will be strict.
I'm sorry. So I guess I really want to. So if C is this category of one object,
yep,
and the endomorphism is K, then I can do this construction.
Okay, hang on. Let's maybe spell this out. So I don't know, maybe we'll call it a trivial example, but it's a good example to ponder. Let's let C be the monoidal category with one object. And endomorphism just being K, right? That was the one that you wanted to. So there's only one object, so of course this object tensored with itself has to be this object, and there's no choice how to make this a monoidal category. This is a monoidal category. But what you can do with this C is you can take its additive envelope. Okay, so now the objects are finite direct sums of the one object. And if you start with a monoidal category, there's a nice way to make the additive envelope of that category into a monoidal category. Well, in this case, you know, what's tensor product? It's just the product of the dimensions there. Okay, and you have to also so this is what tensor product functor is on objects, and morphisms are matrices, but you know how to take Kronecker product of matrices. So this it's totally general. If you start with a monoidal category, the additive envelope is again monoidal. So if we do it for this trivial example, what's the additive envelope of C? Well, that is finite dimensional vector spaces, at least up to monoidal equivalence. So what is a monoidal equivalence? It's a monoidal functor, which is an equivalence of categories. I'm not going to spell out what that means, but you see if you've got a functor between monoidal categories, then they've both got tensor functors, and you want these to be, well, maybe not equal, but isomorphic. And there's some axioms for what monoidal functor is. And so this gives a kind of simple way to kind of present this category of vector spaces, if you like. You know, I can do a little more with this trivial example. It's a good one to think about. This one's strict. This one's not strict. This one's also skeletal. There's just one representative for each isomorphism class here. Maybe I do one more little thing here. I can apply my construction over here and look at endofunctors and natural transformations. And let me see, you can take any vector space. It gives you an endofunctor of vector spaces just tensoring with it. And if you take a linear map, you can just look at that natural transformation between those tensor functors. And this is also a monoidal equivalence between vector spaces and this category of endofunctors and natural transformations of vector spaces. It's important here, remember at the beginning I said that everything is K-linear. So when I say endofunctor, I mean K-linear endofunctor. I don't mean, you know, everyone knows lots of functors from vector spaces to vector spaces, like, I don't know, taking the exterior square or something like that. That's not additive. Okay, so, okay. Good? Okay, so I'm kind of trying to give you some New language, maybe. That's good. Did I use that one? Yep. Did I use that one? Yep. Okay. So I want to talk today really about a slightly more interesting example than that one. That was the trivial example, but we should start there. So the main example for today is going to be, I think I promised this in my abstract. This is going to be the Temperley-Lieb category. I want to give you a presentation for this. Just like I presented vector spaces with this trivial example, I'm going to give you a presentation for the Temperley-Lieb category. So the nice thing about monoidal categories is that you can give them monoidal presentations. So you're going to have some generating objects, and then general objects are going to be tensor products of your generating objects. And you can have some generating morphisms, and then a general morphism will be some picture gotten by vertically and horizontally composing your generating morphisms. And then there'll be some relations between those generating morphisms. It's a very, very nice thing that presenting monoidal categories. The generating objects, well, there's just going to be one generating object. But that means a general object is going to be an n-fold tensor product of that one. Okay, so it's unlike that one where I just have one object straight. Now I've got objects that are tensor products of this one object. And the generating morphisms, well, there's just two generating morphisms, the cap and the cup. And so you've got to be good at this. You've got to read this picture. This is a picture of a morphism from the bottom boundary. This is a dot, tensored a dot. This is this object tensored twice. You see the boundary of this is dot and dot. And at the top there's nothing. Well, that's the unit object in this category. That's the sort of zeroth. That's how I draw the zeroth tensor power of this object. It's just the empty sequence. Okay, so this cap, it's a picture of a morphism from dot tensor dot to 1, and this is a picture of a morphism back in the other direction. This cup. Okay, so this kind of weird, this diagrammatic calculus, but you hopefully get used to it. The morphism is. The name of the morphism is cap, and I'm going to draw it as a picture, but it's a symbol. But that's meant to kind of help you let you see that it goes from dot tensor dot to the unit object. So the diagram is kind of suggestive of what its domain and codomain are. And then what are the relations? Let's see if we can have some relations here. The relations are that. So now I can make these relations very simple by drawing these pictures, because I'm using horizontal composition that's tensor and vertical composition that's... So to read this picture, it's cap tensored... So just a vertical strand, that's the identity morphism from dot to dot. So this is cap tensored the identity composed with the identity tensored cup. And so that it's kind of, if you've never seen this calculus before, it's slick and neat, but those are the only two relations. Oh no. I need one more relation. Right here. Do you want me to say it again in words? Okay, so I'm kind of, it's a morphism from whatever's at the bottom, which is dot, to whatever's at the top, which is dot. This guy in the middle, this is the identity morphism, just kind of vertical string is always the identity. So that's the identity from dot to dot. Whereas this guy, it's cap horizontally composed with the identity. So at this level here, it's cap tensored the identity. And then that's on top of the identity tensored with cup. So maybe I can try and... Do you sort of see that picture as being kind of broken up like that? Okay. So that's saying that is indeed the identity, and the same the other way around. So it's good to do that. This is very important for the game. So this guy here, this is a map from the unit object to the unit object, which is just doing the cap after the cup. So this, I just call this the bubble. This has to be the scalar negative delta. So delta here is a parameter in the ground field that should be fixed.
These morphisms, are these in category or in end of or end?
No, this is a present. This is a generating morphism of this category. It's just like giving an algebra by generators and relations. I'm giving a monoidal category by generators and relations. I'm not taking endofunctors or anything like that. That was. Dot tensor dot is 2 dots. Yeah, the unit object is no dots. Yep. Yep. Yeah. The unit object is kind of the empty sequence, and then you have sequences of length n, and tensor product just concatenating these sequences. Yeah, right. This generates the objects monoidally. So a general object is a tensor product of the generating objects. Including the empty tensor, of course. That's the unit object. Okay? Is it good?
Sorry, can you just say what this is a map from where to where on the right? On the right-hand board?
This one here?
On the right-hand board.
Here. So this is a map from dot to the triple tensor product.
Yes.
This is a map from the triple tensor product back to dot.
So it's a map.
So the composite goes from dot to dot, and that was, that was the vertical composition is doing this.
Can you get the second formula that corresponds to the right squiggle?
Yeah. So that's that tensor that composed with that tensor that. Okay. This is very important. This is a beautiful shorthand, but if you've never seen it before, it can be deceptive.
This one?
This is a strict monoidal category indeed, because tensor product is F tensor G is just sticking them side by side, and if you put 3 side by side, of course, it doesn't matter which order you put them side by side. Okay, so this is a strict monoidal category.
And the squiggle that's a circle, can you write that for me?
This. Well, let me see. What have we got at the bottom? No dots. That's the unit object. At the top, no dot, the unit object. So this is that composed with that. Okay? And so that's just meant to be the scalar. So let's just, okay, so for example, what are the morphisms from the unit object to the unit object? So remember, a general morphism, maybe we should look at this one first. So this is the n-fold tensor product, right? So this would be n dots at the bottom and n dots at the top. We're looking at morphisms from here to here. And all you can do is you can build them by using identities, which are vertical strands and cups and caps. So the only thing you can do is basically you can use some cups and things like that. That's all you can do basically is draw a crossingless matching between the n dots at the bottom and the n dots at the top. And of course, everything's k-linear, so you can take linear combinations of crossingless matchings. That's the whole endomorphism algebra there. Composition of morphisms is just vertically stacking this algebra here. And when you vertically stack these diagrams, you might get some bubbles appearing. But whenever you get a bubble appearing, you just replace it by the scalar negative delta because of that relation. So you see the whole space of morphisms is just, you've got a basis given by crossingless matchings. And so in particular, its dimension is just the nth Catalan number, because that's the number of crossingless matchings between n things and n things. Okay? Or I wrote this down first. What's the endomorphism algebra of the unit object? So I've got to start with the empty sequence and the empty sequence. What can I put in the middle? I can build any kind of closed diagram I can build with cups and caps. But any closed diagram is going to basically be a bunch of, oh no, these are scalars. So that's just the field. Okay. So hopefully that. These are the relations. That's it. Basically, it's saying that two crossingless matchings represent the same morphism if they join the same endpoints. This is just saying you can kind of straighten out wiggles, and so it just becomes the data of what the matching is, not the topology of the picture inside. Does this make a little sense? Okay, good.
Why Catalan's number?
Because that's Catalan's number. I don't know how to answer that. How many here? I mean, I can do like this, or this one, or that one, or that one, right? 5. That's the third Catalan number. You go and okay. Okay. So does it make a little sense? So a general object is n, and another general object is m, and a morphism will just be some linear combination of these crossingless matchings from n dots to m dots. Vertical composition, this circ is just stacking one diagram on top of another. Tensor is just stacking two diagrams horizontally. This is a strict k-linear monoidal category. Okay. That's just a parameter. You picked it at the beginning. It means, in particular, this is the effect of the delta. It means you can get rid of bubbles. Is that? Well, I said something. Okay, guys, I'm going to move on now. Be patient. Okay, I see I've got to say a little bit more about Temperley-Lieb. Yeah. There's no, what is a crossing? You're only allowed to horizontally and vertically compose these diagrams and strings. Well, that's what it means to present a monoidal category. You're only allowed to take the generators and stick them next to each other horizontally or vertically. I haven't given you any generator that looks like that, or any, you know.
Maybe you need to write down this picture as a composition of generators.
Which one? This one? Well, this is the identity endomorphism of dot, tensored cup, composed with cap, tensored. A squiggle in the middle that I pull tight. I mean, okay, I'm letting myself take these vertical lines and slope them because that makes it handier to draw pictures. But you know that whenever that's like what you do with these strings. If there aren't critical points, they're just the identity. When you read in a horizontal slice, you just see a dot. That's the identity map, dot to dot. Can I move on now, or is it still? Be patient. Be patient. Okay, so let me make a definition. I'm going to define a new morphism. I'm going to represent it by this picture. Okay. So what's this a morphism from? Dot, tensor dot to dot. But my shorthand is I'm going to do it as this kind of crossing here. And I'm just going to define it. Let me see now. Gone on my wrong page. I'm going to so I'm going to assume from now on that delta is q plus q inverse for some other scalar q, and I'm going to assume that q has a square root in our ground field. Okay, so that always delta is q plus q inverse. I'm going to define this to be the square root of q times that plus q to the minus a half times that. Okay, so this is a morphism from dot tensor dot to, this is the identity morphism from dot tensor dot to dot tensor dot, whereas this is cup composed with cap. There's another morphism in here. So this definition looks crazy. It's due to Kaufman. And maybe it'll go a little way to say why anyone would care. And then, okay, did I have my relation somewhere? Yes, I did. So I'm also going to define that guy. I'm sorry, it's a little small here. I didn't leave myself much room. The other strand is over. And I'm going to define this to be that guy, kind of, and I'm going to compose it with a cup and a cap in that weird way. So it's sort of kind of rotating that diagram to 90 degrees. Can you sort of see that weird picture? This diagrammatics is very clever. It's a shorthand for a composition, but it's and if you were to work out what that was, you would find that it was q to the minus a half plus q to the half, because it's just rotating the picture. And if you look at these two guys, you find that these two guys are inverses of each other under vertical composition. It's a little exercise, but at some point when you compose these guys, you get a bubble. And bubble is negative q inverse, because that's minus delta. So these guys are inverses. And so what you find, maybe I put it in here. Can you sort of see this is one of those crossings vertically composed with the other crossing. And this is the same composition the other way around. They're inverses, so those two vertical compositions are the identity. Now I feel like this graphical calculus was causing confusion, so I'm so used to it that you see that's just a shorthand for that morphism. That's a shorthand for that morphism. When you vertically stack them, put these two morphisms on top of each other, you have to FOIL it out, and you get a bubble, which is minus q inverse, and things cancel, and you just get the identity, vertical strands. That's this relation. One crossing composed with the other is the identity, either way around. I'm going to try and draw a more sophisticated relation. Can you see that one? That should look like a braid relation if I drew it right. You can check that. And I want to draw this one. Does that picture make sense? So this is the identity tensored with the cap, vertically composed with one of my crossings, tensored the identity, vertically composed with the identity tensored with the cup. This is just a composition built from my diagrams, tensor product and composition. And you should calculate this one for yourself. It's an excellent exercise. You might think you get the identity, but you don't. You get minus q to the 3/2 times the identity. Well, okay, but so what I've got here is I've got various relations in this Temperley-Lieb category. So it's nice that this is a planar thing. That's the point of monoidal categories. There's two operations, so you draw diagrams planarly. These first two, they're usually called Reidemeister 0. This is Reidemeister 2. This is Reidemeister 3. And this one would be Reidemeister 1, except for that minus q to the 3/2, which stops it from being Reidemeister 1. So maybe you've seen a little knot theory and you're familiar with the Reidemeister moves. So these are not minimal. No, the original definition was minimal. Then this was a shorthand. And so anything involving this, these are just more relations that follow. Okay? But when you see Reidemeister moves, you maybe right away see what Kaufman was doing when he, for example, wrote this definition down. You can right away get if L is an oriented link, you can right away get the Jones polynomial, this isotopy invariant of oriented links, out of this Temperley-Lieb category. You see, I mean, so an oriented link, I don't know, is some diagram. might have several components. And oriented means that the components have a direction on them. These diagrams, you can just draw them by, I mean, they are just maps from the unit object to the unit object in the Temperley-Lieb category. They're closed diagrams. They don't have any boundary at the bottom or top. So if you have an oriented link, you can just think of it as being a morphism from the unit to the unit in the Temperley-Lieb category. So it's an element of this thing when you forget the orientation. So it's a scalar. Oh yeah, so any oriented link is a scalar. Why do I need the orientation? What was this pesky scalar? Q minus q to the 3 over 2. If you scale by minus the writhe of the link, so the positive crossing has writhe plus 1, and the negative crossing has writhe minus 1. With the orientation, you can define the writhe of any oriented link, and you can rescale by that power to the writhe, and that exactly fixes the problem with Reidemeister 0. And so you get a number which is invariant under the Reidemeister move, so it's an isotopy invariant of the oriented link, and that's the Jones polynomial. Okay, so I don't know, I feel like that's already a little motivation for why this is something fundamental. Okay. I'm not trying to talk about knot theory in any way, but that's where the Temperley-Lieb category is the star. Okay. So let me see. So this and this, these two crossings defined by Kaufmann, which were just shorthands for this, you know, this wonderful formula. It's very simple, but it's totally wonderful that all the other Reidemeister moves then kind of follow from almost nothing. This is actually, these guys actually define a braiding on the Temperley-Lieb category. So in general, if you have a monoidal category, a braiding, I want the other one. Is some data. For all pairs of objects in your category, it's the pair of data. It's the data of a map from x tensor y to y tensor x, which I've just drawn as this positive crossing, and another map from y tensor x to x tensor y, which I've just drawn as this negative crossing. And these guys have to be two-sided inverses to each other, and they have to satisfy some axioms like Reidemeister 3. The braid relation earlier. So, this is an isomorphism because here's its inverse from x tensor y to y tensor x. This is something that lets you flip tensors. That's a braiding on a monoidal category. And if the positive crossing equals the negative crossing, so that these two maps, they aren't, you know, if the inverse is the original one, it's called a symmetric braiding. So that's what a symmetric monoidal category is. It's a monoidal category with a symmetric braiding. You all know one. Yeah, sorry. That was what I meant. In this case, you would just normally just draw it like this because there would be no reason to distinguish the map and its inverse with the crossing. You all know one example of a symmetric monoidal category because vector spaces is there's the tensor flip from V tensor W to W tensor V. That's a symmetric braiding. Okay. It's you know, I'm teaching you a whole new language, but it's a very simple and pervasive language. You know, everything. Maybe I'll change your lives if you've never seen this language before. You never know. Let's go back to Temperley-Lieb just a second. I'm going to assume from now on that the parameter q is 1. So delta was q plus q inverse. The parameter delta is 2, henceforth. Okay? So then what was our crossing? This was q is 1 now, right? So this is just Oh, both, yeah. But the two crossings are equal now. So now it's symmetric. Okay? So I'm only going to talk about this case from now on. So I've got a symmetric braiding on Temperley-Lieb. So now here's the difficult bit. Everything now so far was sort of easy, and now I need some more adjectives. Somehow I find this subject is heavy on adjectives, and so it's good that there's this book EGNO, that everyone can use the same definitions for these adjectives. So I've already talked about braided. I've already talked about symmetric. I need to very quickly tell you about rigid and pivotal. And so this is the place that it's slightly subtle, and I'm going to try to kind of convey what these adjectives mean. So, but we all know vector spaces rather well, and honestly, it's not much harder than vector spaces. So let's say we've got a monoidal category C, and let's say we've got X, an object. Then there's a notion of a left dual and a notion of a right dual. And so let me try and tell you what a left dual is. Well, hang on, let's think about vector spaces. The thing you all called, I think most of us, well maybe with some group theorists in the room who might write functions on the right. But if you write functions on the left, I'm at that boundary between two generations. I was taught to write things on the right, but I rebelled and I write everything on the left. So let's say we write functions on the left. Then the dual of a vector space is f of v. You write your functions on the left. A left dual, it's a new object together with a morphism from x star tensor x to the unit object. So this might be the dual vector space tensor to vector space going to the field, because that's the unit object, right? It's a new object plus such a map, such that those relations we've seen before. This is saying that this is a non-degenerate pairing. Okay, so and if you have a finite dimensional vector space, yeah, this map would for vector spaces, if you had vi being a basis for your vector space, and if fi was your dual basis for the dual space, so this map would just be evaluation. This map here would be the map from the unit object, which is the field, to vector space tensored its dual, and it's just the map sending 1 to sigma vi tensored fi. That map there, and you can check that these two relations hold. That is exactly saying that this pairing is a perfect pairing between these two. So that's a crucial relation that you all should know and love. So that's the notion of left dual. And the notion of right dual, well, it's just the same, except that the maps are this way. And that was on the wrong side. Oh, no. Yeah. Right dual, you have to put the star on the left-hand side. It's just one of those annoying things. So if you like writing functions on the right, then you know what the right dual of a vector space is. It's just you write v of f, not f of v. Okay, so and same relations. So any monoidal category, there's a notion of left duals and right duals. A given object can have lots of left duals, but they're all canonically isomorphic because the structure of the left dual includes these maps. It's the usual sort of universal game. So rigid simply means that every object has a left dual and a right dual. They needn't be isomorphic, by the way. In vector spaces, they were equal. But in general, the left dual and the right dual can be not even isomorphic objects in the monoidal category. And pivotal, well, no, you want them to really be this equal, you see, so that's really what you want. Pivotal, let me say how I was going to say it. Pivotal is extra data. The pivotal is rigid plus some extra data. Okay, so somehow the definition of pivotal is our main effort today, apparently. And it's quite a subtle definition. Yeah, so you can, well, let me maybe say that in just a second. So let me get this the right way around. So let's say it's rigid. So for every object, I've got both a right dual and a left dual. In fact, you can define this is the left dual. There's the left duality functor. Am I getting my words right? I'm not very good at the right and the left because the star's on the wrong side. This is the left dual. This is the right dual. Okay. So this is actually a functor. Because, well, you take any object x to its dual, x star, but you can also take a morphism, f, and you can take the left dual of a morphism f, and what do? You do right, if f is a morphism from x to y, this is the right dual and the right dual. And I'm getting I hate this stars on the other side. Yeah, this is the right dual because it's the object and the function. Yeah, I've got it right. That's the left dual. I think I've got it right. This is the you look here. This is the right dual, and so I've got to put. Yeah, I'm sorry. It's not. You see, it's not my notation. I'm trying to use EGNO. Okay. So you can do that, and that gives you a functor, and there's also a left duality functor, where you do it that way instead. And if you think about these functors, they switch the order of both of vertical composition and of horizontal. I mean, both of them one's rotating the diagram clockwise, one's rotating it counterclockwise. And so these are in fact both monoidal functors, and in fact they're quasi-inverse to answer Monica's question, these two functors. So left dual after right dual is canonically isomorphic to the identity. Quasi-inverse equivalences. So what's pivotal? Pivotal is the extra data of an isomorphism of monoidal functors from the left duality functor to the right duality functor. I'm going to give examples in a second, but no, vector spaces. For vector space, the left dual and the right dual, they just equal. And in that case, vector spaces is pivotal, and this natural transformation B that this is it's just the identity. Okay? So usually, most of our examples of the pivotal structure B will just be the identity map, and we won't even have to think about it. But it's a sort of subtle issue that you have to deal with. Okay, so let me see. I've got 5 minutes, so I can hopefully say what I want to say.
Do you want some coherence relation?
The coherence relation is saying that this should be an isomorphism of monoidal functors, and you need to know what an isomorphism of monoidal functors is. That is a coherence relation, and as with all these axioms, I'm burying them because typically this is going to be the identity. Actually, we'll typically have something that's strictly pivotal, and there won't even be anything to worry about. Okay. I really need to get to where I want to get to, so I'm going to stop answering that question. Took me longer to explain the Temperley-Lieb category than I was expecting. So, let's say C is pivotal. I've got a theorem. I really want to write the theorem down. But I've got, and let's take a morphism in C, f from x to x. Then there's there's an important definition of the trace of that morphism. So you take your morphism, right? So that's a map from x to x. And so this is x star, the left dual. And there's a given map here coming from the left dual structure. And this is going to be x star, the right dual, and there's a given map there because of the right dual structure. But I need to get from x left dual to x right dual. That's why you need to be pivotal. You have this map B sub x that goes between them. Then you can make, then this is a picture of a morphism from the unit object to the unit object. That's called the trace of f. Okay? Now if you do this for vector spaces with the pivotal structure that's the identity, this is the usual trace of a linear map. This is the field in that case. And then the dimension of x is just the trace of the identity morphism from x to x. And if you do this for vector spaces, this is the usual dimension. This is the usual dimension viewed as an element of the ground field. Yeah, correct. Because indeed it's an element of the field. So let's just, I've got to write down Temperley-Lieb again. Remember, we're taking delta to be 2. And in Temperley-Lieb, well, I've got the cup and the cap. So the left dual equals the right dual. These maps satisfied the relation. So that meant that, yeah, dot is both left and right dual to itself straight away. And what's the dimension of dot? Well, that's just the value of that picture. If I take the obvious pivotal structure that's just the identity map, and because of my minus sign, that's negative 2. Okay, so here's the theorem. I'm sorry that I really want to write the theorem down, because otherwise we end without a punchline, which is never good. So this is a classical theorem. So this is our Temperley-Lieb category. And on this side, I'm going to put rep SL2. So that's just the algebraic group SL2 and finite dimensional rational representations, which sends the generating object to the natural SL2 representation V. Then I've got these generating morphisms, right? But hang on, this V has a non-degenerate form. I guess this is really SP2, and this is just the symplectic form on which is preserved. And I'm just going to send cap to the form. This is my evaluation map from V tensor V to the field, given by taking the form, and this is the co-evaluation map because this form is non-degenerate. This guy here, which remember was that, this just maps to the flip. Just the flip of the tensors. You can make that little calculation. And so all the relations are satisfied. There's this monoidal functor. But hang on a second. In here, what's the dimension of V? What was the dimension of this guy? Oh, that's annoying. This was the wrong pivotal structure. I should have taken the pivotal structure that was -1 on the generating object. So in this bubble, there's a little -1 on the right-hand side, and that fixes it. So this is the right pivotal structure on Temperley-Lieb. And then this is actually a pivotal functor. That's a very subtle place that I thought I should explain that one. That's why Temperley-Lieb is confusing. Okay, so I've constructed the functor. Let's upgrade it just a little bit. Let's take the Caribbean envelope. Caribbean envelope of a monoidal category always has a monoidal structure. This is already additive and idempotent complete. So by the universal property of Caribbean envelope, that functor extends to a monoidal functor on the Caribbean envelope. I want to just change that word to the word equivalence. This is actually an equivalence of categories. Hang on. So in other words, I've taken this, my favorite category, and I found a kind of diagrammatic presentation of it. And the proof is very easy. You have to show it's full, faithful, and dense. And full and faithful is just enough to check it on dot to the n, dot to the n. Where we calculated the dimension on this side was the Catalan number. So you have to calculate the dimension of the endomorphism algebra V tends to n for SL2 and get the Catalan number. Then you have to show that it's surjective on morphisms, but we've got the tensor flip, and you all know Schur-Weil duality that on V tensor n, the tensor flip generates all endomorphisms. So it's full and it's got to be dense. So that's saying that every rational representation has got to be a direct sum of summands of the tensor powers of V. That's only true in characteristic 0. But in characteristic P, direct sums of direct summands of the natural representation V have a name. They are called tilting modules. So if instead of rational representations, I take this subcategory of tilting modules, which I will say more about on Thursday, you still get a pivotal equivalence between the Caribbean envelope of Temperley-Lieb and tilting modules for the algebraic group SL2. And I think now I've overrun a little bit, but thank you.